All right. Hello, everyone. Welcome to my presentation of training AI to see like a pilot. Oh, yep. All right. Is that better? Cool. Thank you. So my name's Eberhard. I'm here from Daedalean AI. And in this presentation, we'd like to talk to you about how we're training AI to see like a pilot, giving a brief introduction about the importance of data for machine learning in general, who we are as a company, what we do, and specifically what we do in terms of machine learning data. So Daedalean was formed about 8 years ago, initially as a startup in Switzerland. Now I would say we're more a scale-up. We have 150 employees. Our headquarters are in Zurich, Switzerland. This is a picture of our lobby in the office. We have a Robinson R-44 helicopter as a simulator and demonstrator, so our employees can have some fun and fly around. But it also actually lets us test some human factors and human-machine interface with some of our technologies, which I'll talk to you about in the presentation. We have a number of different offices around the world. So Zurich is our headquarters. We also have a presence here in the US in Phoenix and an office in Riga in Latvia. We also have pictures of our fleet of aircraft here, our C-182 in the US, Piper Arrow 4 in Europe, and our Robinson R-44 in Switzerland as well. So what does Daedalean do, you might ask? Our main focus is on certifying machine learning for aviation, specifically for safety critical applications. There's never been anything certified for safety critical applications with FAA or the EASA, so our goal is to be the first certified machine learning application. For that, we're working closely together with the FAA and the EASA, so we've done a number of joint projects coming up with these first usable guidances. We've done some projects in Florida with one of our landing systems with the FAA, and with EASA we're developing this process and policies for how machine learning can be integrated into aviation safely. Yes, so we have a number of different technologies, which I'll talk about later, where we actually use machine learning in the cockpit. But all of our technology is based on using cameras installed on the aircraft and a computer on the aircraft to improve pilot situational intelligence. So it's a self-sustained system. We don't have any connection to the outside world in that sense. There's no need for databases or some downlink or uplink. We have the computer on board, which you can see here. We have up to 4 cameras installed on the aircraft, and then a display in the cockpit that can show the output to the pilot. It can be on fixed wing, it can be on rotorcraft, or it can be on unmanned systems as well. And here's a picture of some of the cameras we have mounted on our fleet. So some pictures of the C-182, which we just got the STC for very recently for the installation of these cameras, our Piper Arrow 4 in Switzerland and the Robinson R-44, which we can use not just to demonstrate our technology, which includes traffic detection, positioning, landing system guidance, but also to collect data, which I'll talk more about, and also to do demonstration flights with potential customers and pilots. The system that's installed on the aircraft looks somewhat like this. So we have a variety of different cameras that can be mounted under the wings, either for forward-looking or fisheye cameras, and then a computer box that can be placed in the aircraft that runs all of the software, completely self-sustained with the neural networks on there. So, as I mentioned, we have a number of different technologies. Traffic detection is the first technology that we're certifying with the aim of alerting pilots to any other aircraft that are in the vicinity, or birds, or drones, or anything that might be a hazard. So we're not just looking at cooperative traffic like you might have with ADSB or FLARM, but anything that's airborne in the vicinity of the aircraft will be picked up by our systems and displayed to the pilot. In effect, scanning the sky to help the pilot, so we're supplementing the pilot's observation. So I'm here with a couple of colleagues, Mark as well, one of our staff engineers. We've been collecting some data here at Oshkosh from the ground and running our system on it. So we have a couple of videos that show the traffic detection in action. So we had the simple camera mounted, connected to our computer, and you can see that the system automatically detects any airborne objects. In this case, one of the impressive formation flights from 2 days ago. So the system will draw this box around the aircraft. This is a video that might be then displayed to the pilot, alerting them to where there are potential hazards, other traffic. And on the left, we have a thumbnail that shows the same detection, but zoomed in, so to add a bit of context. And as you can see, it can track multiple aircraft at once. We're detecting at 6 frames per second on this 12 megapixel image. And this is just with a single camera, but we could of course have multiple cameras looking to the left and right for an increased field of view. So this could be an example of what the tablet view looks like in the cockpit. Again, just helping the pilot to scan the sky. Yes, of course. It wasn't super clear, yeah. So yeah, the question was it a hazy day? It wasn't great, but nonetheless we can see traffic to about 2 or 3 miles. But yes, the visibility wasn't amazing. Then we have some more clips. So we moved to another location at one of the reporting points to the west. So again, here the visibility was much better. You can see the system is detecting multiple aircraft that are flying in for the mass arrival. But we also detect these 2 birds here. As you can see on the left, the system is able to pick up the traffic even when it just looks like a few blurry pixels. We only need about 10 pixels in order to get a good detection. And of course, anything that's larger than that is even easier to detect. And we have nice, robust tracks as the intruders cross the field of view. And just some more examples. The nice thing, of course, at Oshkosh is there's so much traffic. We didn't have to wait too long to collect this data. Not just for demonstration purposes, but this is data we can now use to continuously improve the system. Yes? For ranging? That's a good question, yes. So the range estimates here are, at the moment, they're work in progress, so the numbers here don't actually reflect the actual range. We do have a category and range neural network in addition that we can run. We didn't run it on this. And that would look at, it would identify what kind of aircraft it is, if it's a helicopter or an airliner. So it knows at that pixel size, it will be roughly that far away, and use that to estimate and predict the distance. But here it's only running the detect neural network. And I'll talk more about the neural network architecture later on. Yeah, just some more examples. And I think one nice example here as well, there's a road here, so the system doesn't just look at any moving objects, it's specifically trained only to look for airborne objects. Also, if there's people or anything else moving on the ground, it won't detect those. And one last one here is an example. The cars going by don't trigger any detections, but we're robustly seeing anything in the sky. All right, so the next video is an example of an integration we did with Leonardo, a project where we implemented our hardware and software onto 2 of their helicopters in some test flights in Poland. So please enjoy this short video.
There are so many challenges in aviation, but the lack of situational awareness is one of the major causes of accidents on helicopters. The Daedalean has maybe the technological answer to this need.
The Daedalean system provides situational intelligence, the ability of the system to understand the environment and make sense of what's happening around it.
We are here in Leonardo Helicopters PZL Swidnik to evaluate the capabilities of the Daedalean products on SW4 Solo and SW4 in order to deeper understand what happens in real environments.
Within Leonardo there is a research facility which is called Leonardo Labs. It's a constellation of different labs tackling problems from AI to quantum computing to autonomous flight. We don't have too often the possibility to test technologies on actual helicopters, and especially AI-based algorithms coming from the Daedalean.
The Eureka Eurostar grant allowed Leonardo and the Daedalean to work together for the testing of innovative computer vision and artificial intelligence technology. We are excited to bring them to the next level of pilot assistance and automation. The visual awareness system has 3 main components. The first one is the sensor suite, the cameras. The second one is the processing unit that runs the neural networks. And the third one is the user interface. Artificial intelligence is the power that is behind this technology. With the traditional algorithms, we couldn't possibly do what we do with artificial intelligence. We are embracing the challenge of certifying these technologies in the direction of pilot assistance and autonomy. The visual awareness system from the Daedalean tells the pilot where the traffic is, not only traffic you can detect with ADS-B, TCAS and other transponder, but it also detects things like birds, what we call noncooperative traffic. The system guides the pilot into a safe landing. Or we can tell also the pilot where it is, so the global position of the aircraft, even when the GPS is not working.
It's not easy to find partners who has such kind of advances in AI in aviation. As well, it's not easy to find a helicopter manufacturer who would actually push the limit of innovation and try this kind of technologies in real use cases on real helicopters.
This partnership between the Daedalean and Leonardo was really fruitful, in my opinion. It allowed us to see the Daedalean system firsthand on board our helicopters. And this is only a first step, because in my opinion, now that we have more data and a better understanding on the Daedalean system, we can also start a longer collaboration with them.
In the future, we'll be able to have many flying objects in the sky, so such a system like a visual awareness system will be very useful to organize and manage this in a especially urban environment.
As Leonardo, we know what our customers are demanding and will demand in the future. This partnership is a milestone to bring new capabilities inside the aviation. We want to go beyond the pure research and start to build products for our customers.
All right, so that gave a brief introduction to some of our technologies and how it can work. In the next couple of slides, I'll go into more details about each one individually. So first of all, the visual traffic detection, as I mentioned, it's what we're certifying first. So this will look for anything in the sky, be it cooperative or non-cooperative, from airliners, fixed-wing rotorcraft, drones, birds, balloons from a wedding, anything that's flying in the sky. The pilot will be alerted to that with this bounding box and display it on a tablet. As I mentioned, detection range is about 2 to 3 nautical miles, or with airliners, of course, even further because they're much bigger. At 6 frames per second, so we're taking 6 pictures per second, effectively scanning this whole field of view multiple times and supplementing the pilot's scanning ability. And ultimately, of course, the pilot is then still piloting the aircraft. We're just increasing the situational awareness. And we can track multiple objects. So as you saw before in the Oshkosh videos, we can easily see anything and also allow the pilot then not just to find where that object is in the sky, but sometimes if you have multiple other traffic in the area, I'm sure you know it can be hard to keep track of all of them if you're also in a pattern. So here the system will just help make the pilot's life easier. And the system works in a variety of conditions. We're certifying it for daytime VMC at first, but even so it works in limited visibility with haze, against cloudy backgrounds, at low light as well, so for dawn and dusk is no issue, above and below the horizon, and at any different trajectory, so we can see intruders regardless if they're coming head on, if we're following them top or bottom. We are training the neural networks to see it in all conditions. And we also have wire detection. This is something that we've started working on slightly more recently. It's particularly interesting, of course, for rotorcraft. It's still one of the leading causes of accidents with power cables, telephone lines, anything else, especially in mountainous areas. And we're based in Switzerland. We have a lot of valleys with power cables that are strung across, or farmers that will overnight put up some metal cables. And even if you're very close, as a helicopter pilot, it's very difficult to see the power lines or the cables. So this system, just like the VTD, it's scanning the video feed that the cameras pick up and then highlighting not just the cables, but also the masts themselves, so that the pilot knows where there might be a danger. And this is also something that we have flying on and installed on a variety of aircraft, and it's will probably be the next certification, I think, after the traffic detection. Then we have the visual landing guidance. So this is looking for runways to help the pilot detect the runway, see where it is, but also output where the aircraft is on the glide slope. So similar to an ILS in a way, but of course this will work on any runway even without ground infrastructure. Again, it's our standalone system that's completely, that's not relying on anything else, installed on the aircraft. So you can go to any runway and the system will see it, tell you where you are, if you have to go left, right, if you're too high or too low. And yes, we also have the vertical landing system, so similar to the conventional landing, but here for rotorcraft, using any marker on the ground, we can detect that using the fisheye camera, and again, tell the pilot where they are relative to their chosen landing site. One of our other projects or products is the landing site finder. So this is then running in real time to look downwards again and show the pilot suitable landing spots where there aren't any objects, any vegetation or vehicles, so be they stationary objects or dynamic objects. In the case here on the left, for instance, this vehicle is driving through, and so the system will automatically see that this spot is no longer a suitable landing spot. And finally, we also have the visual navigation. So this is using the downward-looking camera as a backup to GPS navigation to allow GNSS independent navigation. So either in the case that your GPS gets jammed or you lose signal, we can bridge that gap, or you can fly completely autonomously from GPS using this visual navigation system. So it works either on pre-surveyed maps. So we learn which features are in a specific area and then look for those with the downward-looking camera to identify where the aircraft is. Or we can use satellite imagery. Or we can even fly in an area we've never been in, and it will look at the images and then determine from how the image is changing how the aircraft is also moving. And again, this is completely standalone, doesn't rely on any signals to the outside world. And very recently as well, this May, we integrated a number of these technologies onto a OH-58 of Moog in Mineral Wells, Texas. So here's a short video that shows how our technology can be integrated into an FMS and autopilot of a helicopter. So with this project, we were able to fly a 70 nautical mile loop with our helicopter without GPS signal, just using the visual positioning system to an accuracy of a few feet, coming back to the landing spot, and then landing at the landing site with the vertical landing system, all by feeding the output of our visual positioning system into the FMS and the autopilot, effectively giving a backup to conventional GPS navigation. So this is all based on machine learning. I don't want to get too technical in this talk, but I do want to give a brief overview of how the system works and the underlying technology. So as I mentioned, it's all a standalone independent system. We have this computing hardware on board, and the neural network is just one small part of this. We also have conventional software, of course. But the neural network component of our system takes the camera input, which is filming the outside world as we're flying, applies some pre-processing to that, and then runs the neural network on this image. And the output of that is then simply an indication either on the tablet that the pilot sees, the bounding box, for instance, around the intruder, or then coordinates telling the FMS where the aircraft is. So the neural network is just one small part. And of course we use AI, but it's not AI like ChatGPT or generative AI. Our artificial intelligence is better described as machine learning, because in effect all we're doing is supervised learning, teaching the neural network to look for patterns. So I made this small, simple example of how supervised learning works. So let's say we're trying to teach a neural network to detect a cat. So we're trying to build something that will tell you, if you feed it a picture, is this a cat or not? So the first stage is the training phase. So this relies on a large data set of images that we know have cats in them. So in this case, a human has looked at this image first, said, yes, this is a picture of a cat. We feed that into the ML training, and by looking at thousands and millions of images, the neural network looks at all the patterns, the shapes, the colors, all the relationships between the pixels, even things that we as humans might not necessarily notice, these patterns, and it will then effectively learn what kind of patterns does a picture of a cat exhibit? With this trained neural network, we can then feed it pictures that it's never seen before. So in the real world, we might then be walking around with a camera. We see a cat walking across the field of view. And it will then, having learned what a cat is supposed to look like, look at the picture, look for those patterns that it's learned. And if it is a cat, then it will tell you, yes, this is a cat. If it's anything else, then it won't. So the machine learning is, in that sense, it's quite a simple thing. It's pattern recognition, looking at lots and lots of images to find out what makes a cat and what does not make a cat. So that's effectively what we do. We're showing it pictures not of cats, but of helicopters and fixed wings and airliners and birds from across the world, and letting it learn what these look like. And of course, with our traffic detection, there's a lot of parameters that can affect what the image will look like. We want to work across all of the United States and Europe, and later on across the whole world. So we have to feed in pictures not just of all the different aircraft and objects we want to see, but the different backgrounds and weather conditions. And for that, we have this so-called operational domain. Here, we've identified a variety of different parameters that can affect the appearance of the image. And in order to collect a big enough data set to actually get the performance that we want, we have to collect data across all of these parameters. So I've just selected a few of these because otherwise it would go on much long and in too much detail, but I think these examples are quite nice to demonstrate the kind of data we need. So for intruder, we have category and range. We want the system to learn all the different categories of flying objects that it might encounter in real operation, and also ranges. So, of course, we have to collect data of different types of aircraft. Here we have some examples of our data sets of general aviation, of birds, and of rotorcraft, all of which, of course, look very different. And at the same time, we don't just want all the different intruders, but also the same intruders from different orientations and different attitudes to get the completely varied data set. In terms of ranges, so this is an example, same intruder, but at quite a large distance and then much closer. So as long as it's more than 10 pixels in this 12 megapixel image, we use it for our data set, all the way up to as large as we can see it. And of course, the on-chip altitude also makes a difference. So here we have an example of a few hundred feet above the ground, up to about 20,000 feet. The visual appearance of the image varies quite a bit depending on how high we're flying. And again, because we want the system to work reliably in all conditions that it might be flown in, we need data from across this whole spectrum of altitudes. Then we also have the local time and weather, which has an effect, of course, on the performance and on the visual appearance of the image. So when we collect data, we're not just flying when it's perfectly clear sky and perfect conditions at noon. We're flying from dusk until dawn in any VMC conditions that we can see. And also ecoregions. So for this, I'll go into a bit more detail. Ecoregions are defined as areas with specific vegetation, land use, ecology, geology across the world. So the entire world is split up into these so-called ecoregions, and that combination of land use and vegetation gives it a very unique appearance. So we can say that, for instance, this northern short grasslands in South Dakota, I believe, this has a visual appearance that can only be found in this area in the world. Similarly, the Appalachian mixed forest has a certain appearance that can only be found in that area. And because we want the system to work in all conditions and all areas, we collect data from all of these ecoregions, because an intruder flying across this background will just look different than in a different region. So here's an example of the ecoregions that exist in the United States. Every color is a specific ecoregion. And our goal is to collect data in all of these. So it's quite a large undertaking. It's a lot of work. But that's what we do to make sure that the system will reliably alert the pilot of any traffic. So in total, I think there's about 84 in the continental United States. This is where we are so far. So green means we've collected sufficient data according to our requirements that we set for ourselves, where we say we need a specific amount of hours of data per ecoregion. Yellow and red, we're on the way, and white is still to do. So here at Oshkosh, we're still in the red, so we got some more data already. This will hopefully soon turn green. And this is an example of the flight path that we've flown in the last couple of months across the US with our C-182 here. Mostly based out of Wichita for now, but soon we're going to start flying from A to B across the 48 states. And I think today we're actually flying to Chicago with our plane. So with these flight paths, we aim to cover all of these ecoregions. We don't have to fully cover a state, so it's not like survey flying, but we want to get a sufficient amount of flight hours in each of these areas. And here's another view. Each of these dots corresponds to one of the flights we've done in the US. So here we actually have some additional dots that weren't in the previous map. They were with a previous generation of cameras. But even so, we've already covered quite a decent area, a lot of data, a lot of flights, but that's what's needed for this certifiable machine learning. Similarly, in Europe, we've of course also done flights with our helicopter and fixed wing there. A lot in Switzerland, but also in neighboring countries, and this is something we're continuously expanding. So in total, we've flown 100,000 nautical miles. That's about 5 times around the world. We have 200 million images in our data set, 1,300 flight hours so far across 3,300 flights. And continuously growing, of course, because the more data we have, the better the system will perform. And to collect all this data, we've installed our system on a number of different aircraft. So we have our Robinson 44 in Switzerland in our fleet, which we use for data collection, flight testing, but also demonstration flights to show people these technologies live. We have an AS350 in Switzerland as well. We've integrated our system on Leonardo helicopters in Poland and with Genesis Moog's Kiowa, as we saw in the video before. We've also flown in Brazil with Embraer's Bell 206, but also on a number of different drones. In terms of fixed wings, we have our own Piper Arrow 4 in Switzerland. We've also mounted our system on a glider, because this is one example where we realized one of these parameters is the intruder category, and we realized we don't have enough data of gliders yet, and so we want to make the system see those better. So Mark, who's a very accomplished glider pilot, kindly put the camera on the nose of his glider and entered into a gliding competition and collected quite a lot of data for us. We have our 182 here in the US. We've mounted our system on Eclipse's business jet in New Mexico, so that let us go up to 20,000 feet, flying at 350 knots, pushing the envelope of the data that we've collected. We're on a C-208 and another 182 in the US, just to name a few. In total, I think we're at about 40 different platforms so far, and this is also continuously growing. We've also mounted the system on a hot air balloon, again thanks to Mark. In a similar case to the gliders, we realized we didn't have enough hot air balloon data yet. So again, we entered the hot air balloon championship and had our cameras mounted here. So now I'd like to just dive a bit into how we actually do these data campaigns. For instance, when we realize we don't have enough data of hot air balloons, or we don't have enough data from a specific area, or in the example of Wichita, for instance, this ecoregion was red in the map before. That means in the next couple of weeks, we're going to be flying here and collecting the data that's still missing. So it all starts with campaign planning of these data campaigns. So we'll look at that map from before, which looks at our current data set, sees, okay, we need maybe 3 more hours in Wichita. And then the data team will plan these flights to cover the area. So here's an example from ForeFlight with an example of a flight route that we might do in order to get this missing data, flying here into Oshkosh. So this will be done partially in headquarters in Zurich. Then we'll see about crew availability, aircraft availability, put that all together and start planning these flight missions. So our crew consists of 2 people, a pilot and a recording instrument operator, or RIO for short. So we'll assign these crews to the missions, usually about 1 or 2 weeks, where they'll fly a specific area in the US or Europe. So the pilot, of course, is tasked with flying the aircraft safely, but also assist with the route planning. And the RIO is the representative of the data team. They will take the data demand from the ML engineers, bring that with them, assist with the route planning, with the campaign planning that I showed before, do the entire system preparation and operation, since we have this hardware installed on the aircraft, and also the entire data management. So a typical day might look like this. The crew will be in a hotel close to the airfield, discuss their mission for the day. They might be in Wichita and have to fly to Oshkosh, for instance, so they'll discuss the route, look at the weather, propose alternatives if necessary, and do this briefing in the morning, and then transfer to the airfield. The pilot will be responsible for the pre-flight check, making sure that the aircraft is operational and ready to go, and the RIO will do the entire system check, doing a ground check of the system and hardware, looking at the software, making sure that the cameras are clean as well, of course, because we want as high data quality as possible. And when that's all good, the crew is ready to go for the mission, so they'll take off and start flying towards their destination. In flight, the RIO is responsible for operating the system. So this is operating the recording mode, filming and recording everything that the multiple cameras see. Of course, both crew members are responsible for the navigation and discuss any possible in-flight reroutings if necessary, and operating the flight as you might in a conventional flight. But the RIO will also take notes of any events that occur during the flight. If there's any interesting events or specific traffic that's seen, they'll enter that into the recording notes as well using this tablet that they have. And on the picture here on the left, you can also see we have the tablet mounted in the cockpit of our C-182, so we can operate our entire system right there from the cockpit. And finally, after the flight, there's a post-flight system check, so the recordings are saved, and we record more than almost 2 terabytes per hour, so we're generating a lot of data, capturing these 6 frames per second across multiple cameras. So we usually fly around 2 to 2.5 hours before we land, and then put in new drives to make space for the next flight. So that's also something the RIO is responsible for, this data management. So we're filling up multiple drives. We have a whole box on the aircraft with spare ones. And after the flight, they'll swap these out, and then also clean the cameras, because as anybody that flies an aircraft knows, even in short flights, you'll get bug strikes and dirt on the aircraft and dust. It's the same thing for our cameras, so we always have to make sure that this is cleaned. Although it's important to note that even with these bug strikes, the system is robust against these. So we've landed sometimes with the camera really covered. This is, I would say, a medium example. We've had much heavier strikes, and even then the system still operates. We're still able to detect traffic, so we're very robust against this. So once the data is downloaded and on these drives, we'll either upload it locally from where the aircraft is, or we'll ship the drives back to Zurich, to our headquarters, where we have our in-house tools for logging all our flights. So these 3,300 flights at the moment are all in the flight log, where we can track exactly the recording notes, where we flew, what features we used in the flights, and again we have a map to show where we've flown. And then, in order to actually use the data to train the machine learning network, we have to do manual annotation. So it's all our data is looked at by humans, and the neural network is only trained by what humans have seen. So there's always humans in the loop. The system isn't learning by itself. It's all reliant on what a human can see. So annotation is the process of where our team in Riga looks at every single picture that we've collected, and which is very time intensive and very laborious because, as I mentioned, we've collected 200 million images, all of which have been looked at by humans, and they're looking for any objects that might be in the field of view. So in this example, we have an aircraft in the bottom left. So they'll see this, and then they'll draw a box around it, and then that's used for that data set, like the cats I showed you earlier, that the system will then look at and learn to identify what an aircraft is. So they go through these hours and hours of footage drawing these boxes, and I think in this case it's quite an easy example, but some of the data is a bit more tricky. So here's a frame from the hot air balloon championship that I mentioned earlier. We have more than 100 hot air balloons in the frame, and each of these was labeled manually by humans. So it's a lot of work, but it's something we have to do, not just for the certification, but to make sure that the system is really operating as we want it to. And then, of course, it's just the training beforehand. When the system is in operation, it will use this, everything it's learned to then, in the real world, identify things independently. After the annotation, we have a separate process where we then inspect the data by a separate team. So once again, all the frames are looked at by different people. This is just to make sure that we have an additional step in the quality assurance, just again in the pursuit of high quality data. So here the inspectors will look, does the box really only include the aircraft and nothing else? We don't want the system to learn anything about background or things that don't belong to the aircraft. And we also have this plot here that shows the size of the bounding box over time. So any anomalies would be identified here and then sent back to the Riga team for rework. So it's a lot of work, but it's something we have to do again for this high quality data. And then once, yes, sorry. Yes, so exactly. To help the annotators, we also record not just the visual imagery, but we have ADSB coming in and the other sources, GPS, AHARS. We record other sources of ground truth and also the ICAO addresses. We will then use that to, in the frame that the annotators are working on, we know, oh, roughly in this area of the image we expect there to be traffic because we got the ADSB signal. We know where our aircraft was at that time. We know the attitude. We know where the intruder is, so we can do this hinting, and then exactly we can match, was this aircraft the same one with the same ICAO address? Yeah. Of course, only for cooperative traffic. Anything non-cooperative like birds won't have that. Yeah. Yeah. So we use additional sources. Yeah. So after the inspection, if everything passes, this data set is then passed to our engineers, who use it to train the neural networks with the supervised learning process that I showed you before. And that's how we continuously improve our neural networks. So at the moment we have the system flying across the world, as I showed, installed on different aircraft. With the data that I showed that we collected here from Oshkosh, we're able to detect any variety of flying objects. But still, we keep collecting data to cover these new areas and expand the data set. So our goal is to have the certification for traffic detection this year. We've already entered the 3rd stage out of 4 with EASA and the FAA for these stages and involvement, these audits that we do together with them. And we're defining how AI, how ML can be explainable and certifiable, again, to reach this first certified machine learning for safety critical applications. But luckily, we need a lot of data, of course. Luckily, we can also use synthetic data to supplement all the real world data we collect. So in this example, one of these images is real and one is synthetic. So we have some very smart people at the company that are able to remove real objects from our data and then put in a basically synthetic target, so a computer-generated target, which we can also use to train the neural networks. And we've shown that we can train a model on synthetic data, show it real data, and it will detect everything. So we're able to prove that training on synthetic data does not have any negative effect. In fact, it improves our data sets. It allows us to collect data that we couldn't collect realistically or safely. Head-on encounters, for instance, we don't want to do in real life. So this allows us to expand our data set very easily, also with rare intruders that we might not see, or combinations of locations, intruders, daytime, weather conditions. So perhaps you can try and guess which one of these is real and which one is fake. Who thinks that the left image is the real one, for instance? And who thinks that the right one is real? So you're quite good, yes. The left is indeed the synthetic image here. But again, I think it's really quite impressive what our engineers are able to do. Here's another example where one is real and one is synthetic, this time of airliners. So in this case, the left image is actually the real one and the right one is simulated. And one more here where the right image is the real one. So this is a cost-effective way to let us expand our data set, but we still need the real data, because for the verification of the system, we only use real data because that's what the system will see. Synthetic data is only used for the training of the system. So that's the end of the presentation. I do have a short video after this slide as well. And then, of course, I'm very happy to answer any questions you might have. Yeah, it was very nice to share how we collect data and why we collect data. So I was at Eberhard, the head of data at Daedalean. And here's a short video showing how Mark collected this glider data.
Daedalean is teaching a computer to see gliders by surrounding a glider with gliders. This is Mark. He's an expert glider pilot and an intern at Daedalean, where we're developing situational intelligence, which is basically the ability of a computer to keep aircraft safe using AI. To help us get there, Mark had an idea. He built a custom camera housing, installed a Daedalean computer, and took flight in a series of competitions over the course of a summer. The camera's aerodynamic disruption definitely wouldn't help his chances of winning. But Mark had a different goal. With the camera rolling, Daedalean's visual traffic detection system recorded every glider that came into frame, each one teaching the computer a little more about what a glider looks like. AI-enhanced algorithms process and analyze the video, pixel by pixel, to gain what's called semantic understanding, the ability of a machine to process the meaning and context of real-world information. The more video recorded, the better the semantic understanding. With his competitors whizzing by, Mark stayed aloft for as much as 8 hours at a stretch to make sure the computer saw lots of gliders. Because this is very personal for Mark. He knows that a significant number of fatal mid-air collisions involve gliders, even though they fly only when the weather's nice, just a few months a year. Collisions often happen when a pilot doesn't see the glider until it's too late. But it's Mark's hope that one day, aircraft will be outfitted with Daedalean's computers, because if they were, they could spot a glider well ahead of danger. And they could spot all sorts of aerial objects, not just gliders, drones, paragliders, hang gliders, skydivers, and even birds, in addition to airplanes and helicopters. The skies would be safer for everyone. As the summer sun faded, Mark's competitive season came to a close. On top of recording heaps of glider video, A second and fifth place finish made this summer a success by any measure. But with the internship ending, Mark's sights were focused on his future. And ours were too. We weren't about to lose someone with his initiative, talent, and determination. So we brought Mark on board as a full-fledged, full-time Daedalean employee. We're looking forward to what he comes up with next.
Yes, Mark is here. It's also responsible for all our data campaign planning and flight operations for data gathering. So if you have any questions, I'm sure he can answer those as well. And otherwise, please also ask any questions. Thank you for your attention, and thank you for coming. Yes. So at the moment we're in certification. We haven't defined the price point yet. It depends on the use case and of course which of the technologies we integrate. I think for general aviation it might just be for the VTD. For integrated in FMS it will be a different product, but that's something we'll define later on. Yeah. Yes. We do have performance guarantees that we need for the certified system. It all depends on, has the object been identified on this frame or on a previous frame, or is it the first time we see it? So we're at 98% for each frame, but we also detect multiple times per frame, 6 times per second. So if one of those is maybe not detected, then the next 1/6 of a second it will be. So in effect, the 98% actually ends up being much more robust. So, and for false positives, we also do have defined limits, and that's something that in the verification we make sure that we meet that performance. Yeah. Sorry. Yes. Yeah, the tracks. Yeah. Yes. Thank you, Mark. Yes, so the question was, do we use, what is these false positive performance ratios, and how do we make sure that, like, do we have a certain target that we try to reach? Yeah. Yes?
In addition to detecting objects, are you planning on using track information to predict potential collisions?
Yes, that's a very good question. So the question is, will we use track information to predict collisions? Yes, that's something we already do. I forgot to mention it. So we calculate the time to collision if there is a collision trajectory, and also display that. Also using, we know what kind of category the aircraft is, what their performance is, how they might move to take that into account. Yes. Yes.
What's the weight of the equipment?
Yes, so the weight of the equipment, at the moment it's roughly 2 or 3 kilograms, so maybe 5 or 6 pounds. The compute box itself, let's see, here. The box itself is roughly a couple of pounds, 3 pounds perhaps. The camera is about 1 or 2 pounds. So if it's installed, for instance, on the Robinson R44, we have it on a micro mount on the nose. It has a negligible effect on the CG. Yes?
So you mentioned that you use ADS-B during your training. In the final system detection, would you be cross-referencing that as well to know where to expect to see something?
We work independently. We can also take in ADS-B and hybridize that. For the certification, we're not taking that for the, let's say, when the system is in operation, but it's something that we can do as well, yeah. Yes? Active sensors, well, what kind of sensors do you mean? Sorry, I didn't quite hear. I'm not quite sure what you mean by active. As in, scanning like LiDAR or? Yes, we have. For VPS, for the vertical landing, for instance, we also laser altimeter or LiDAR. We have considered. We also are working on different sensors, not just the visual cameras we have now, but infrared, for instance, to expand that. But for now, our detection is purely based on these cameras. So we have multiple miles of range where a LiDAR would only work at closer ranges. Yes, at the back? All our data is in the headquarters in Switzerland. We have it also backed up off-site on tapes because, of course, the data, there's a lot of money and effort that's been put into collecting this data, so we do back it up, and it's all stored on site. At the moment, we use it ourselves, but in the future, we might make this data set partially available to other partners and companies because it is our biggest asset.
Just to check, is all of the computing done on board? Is there any need for data link or off-air?
No, so everything, all our technology, all these features I've showed you, the traffic detection, wire detection, positioning, it all runs completely standalone on this box. So the aircraft is completely independent from any data link, any data sets. The neural networks we train are, as I showed, one component that's of the software of this box. So all the training is done beforehand on the ground, but then once it's loaded on the system is ready to go anywhere regardless of signal, so completely self-contained. Yes?
I'm a little confused why you have to take so much terrain data. Is that only to identify the terrain and extract it when the moving target is below the horizon?
Yes, exactly. So we need all these different ecoregions and terrains to prove that the system works in any condition. So we are, of course, only learning on the aircraft, but if it's flying below horizon in front of snow or a desert or a forest, it will look a bit different. So that's why we've set this goal for ourselves too.
Isn't the background data more dependent on whether you're looking at an urban background or a farmland as opposed to I'm in Wisconsin or I'm in New York?
Yes, exactly. So you're right, the background is not just the ecoregion, but also the background type. So the other one I blurred here is not the ecoregion, but background. So exactly like you mentioned, urban backgrounds, for instance, are also something that we specifically target. And even if we collect empty frames, we can then use these backgrounds to put in the synthetic object. So, yes. I didn't quite hear the first part, sorry, if it's as good as... Oh. The system on board is as good as the last update, so the certification process is quite intense, I would say, so we really make sure when we train a neural network and release it that it's good enough. And then, of course, in the meantime, we're working on the next update. But yes, we use the data we collect to train the next one, but those are then released as updates, so yeah. Yes? The power consumption, that's a good question. I think on this generation we're at about 20 to 30 watts with multiple cameras. Of course, something we're always reducing, but it's already quite low. Yeah. Yes?
Are you considering using this on drones for autonomous navigation for your GPS design?
Yes, we are considering using this on drones. We have used it on drones. Let me just quickly go back to the other frame. So I've been talking here mostly about how we can assist pilots with situational awareness, but for navigation, for instance, for traffic detection, for wire detection, that is something that we can and have put on drones and other autonomous vehicles, which can then be fed into their own flight controls, yes. So this, for instance, the visual positioning system, the output is coordinates. So if it loses GPS signal, it can bridge that gap with our system, and the system is small enough to be fitted on medium-sized drones at the moment, let's say. We have another generation that we're working on that works on something the size of a Raspberry Pi, so that's even easier to integrate on drones. All right, well, sorry, yes. That's an audible warning is something we could add. At the moment, we'll have the screen with the bounding boxes, it's also a question for human factors. How much would we distract the pilot? We don't want to overload the pilot, of course. At the moment, it's a visual alert, but depending on the use case, we can change that, yes. Yes? So our plans for operations in IMC or nighttime, as I mentioned, we're also working on infrared sensors for low light condition and night conditions, so that would work there. For IMC or partial IMC as well, with infrared we can look through certain haze and fog. So that's something we're expanding into as well. But the first certified product will be for daytime VMC. But yes, expanding our operational envelope, including nighttime and low light IMC is something that we're working on. All right, thank you very much. And of course, feel free to come up and take some of our flyers or chat with us. We're happy to talk.